Welcome back. Today, we're looking at the synthesis of 4-benzylidene 2-methoxazole 5-one. We're going to be calculating its overall percent yield, determining the purity of the product that we synthesized in the lab, and finally, we're going to be looking at a potential byproduct that can happen if an unwanted reaction occurs. After that, we'll check out our own synthesis, where we create our own synthesis reaction. Let's take a look at the synthesis reaction of 4-benzylidene 2-methoxazole 5-one. First, let's calculate the overall percent yield of this multi-step synthesis reaction. This is done by calculating the percent yield of each synthesis step and multiplying them all together. The first step of this process is to find out the limiting reagent of each synthesis step. This is done by using the amount of each reactant we have and calculating how many moles we have in the reaction of that compound and comparing that amount of moles to the amount of grams we have to all the other reactants in our synthesis. For the first step of the synthesis, glycine is the limiting reagent. And for the second synthesis step, we have potassium carbonate. Now we have to calculate the percent yield of each synthesis reaction. For the first synthesis reaction with glycine as our limiting reagent, we get a percent yield of 63.07%. And for a second synthesis using potassium carbonate as our limiting reagent, we get a percent yield of 30.91%. Multiplying these 2% yields by each other, we get a total percent yield of around 20%. Let's check out the tests that were done to assess the purity and the composition of the product that we got from this synthesis. Looking at the melting point, I would roughly say that's around 142 to 152. Looking up literature melting point of our product that we wanted to synthesize, it gives us a melting point on SciFinder of 151 to 152 melting point that is stated, but that is probably due to some contamination in our final product. The compound that I looked up on SciFinder was the Z isomer, which had that melting point. So given that we had around the same range, we most likely have synthesized the Z isomer of this product. Looking at our IR that we received, we have a couple of peaks, very small ones at 3,700 and 3,052. Strong to medium ones at 1,771, 1,653, and 1,259, which corresponds to the benzene ring, our carbonyl carbon double bond, the nitrogen bond, and the ester bond, respectively. Looking at a literature IR value of our Z isomer compound, everything seems to line up, except on the literature IR, there seems to be a broad signal between 2,800 and 2,900, which usually corresponds to an sp3 hybridized carbon hydrogen bond. Given that the reaction has not come to completion, which is probably why we are missing that sp3 hybridized carbon hydrogen bond. So overall, it looks like we have almost fully synthesized our product with some contaminants, and the reaction looks like it might have not fully gone to completion yet. There's sometimes an unwanted product that occurs when our wanted product reacts with water at high temperatures. We were told that the melting point of this unknown compound is between 193 to 194 degrees Celsius. After looking for a very long time, I was able to come across a paper that was synthesizing the product that we were looking at, the azlactone, and they also reacted that product with water under high heat to synthesize a compound that they called alpha-acetoaminocinamic acid, or alpha-acetoaminocinamic acid. Researching this chemical more, I looked at a website called chemicalbook.com and found the melting point for this compound, which was stated at 194 to 195 degrees Celsius, so only 1 degree off from the stated temperature of the melting point. So with the information that was given to me and the information I found, I was able to say that this was in fact the product that came out of this reaction that we were supposed to look at. So here I drew a potential mechanism for what I think happens in this reaction. Water attacks the carbonyl carbon, pushing the electron up onto the oxygen. This water, now attached to the carbonyl carbon, has 2 hydrogen bonds as well, so it is holding a positive charge. Another water molecule comes by and takes that proton from the water molecule attached to the carbonyl carbon, creating a hydronium ion and stabilizing the OH group, which is now attached to the carbonyl carbon. The oxygen puts its electrons back onto the carbonyl carbon to create the double bond again, which pushes the electrons connecting the carbon to the oxygen, which created that ester bond, to the oxygen, breaking that bond. Since this oxygen is in a vinylic position, it is then resonance stabilized with that double bond of that alkene, connecting the carbon to that nitrogen. That nitrogen then can attack a proton from the hydronium ion, which results in our final product of alpha-acetoaminocinamic acid. Now, let's try our own synthesis of this compound to this compound. Oh wait, that's for another video. We want to synthesize compound M from N-butyl acetate using any of these compounds on this list. Now, looking at those compounds, we can see a similarity between a lab that we've already done, that is the Claisian condensation. We can react N-butyl acetate with benzophenone with 1 molar sodium ethoxide in ethanol to create compound M. Now, we want to produce 35 grams of compound M from our starting reactants. To do this, we first have to find out what the limiting reagent is. To do this, we start with a set amount of grams for each reactant and then see how many moles we get from each of those compounds. Whichever one gives us the least amount of moles is our limiting reagent. So with the calculations, we see that benzophenone is our limiting reagent. Now that we know what our limiting reagent is, we have to find out how much of it we need to produce that 35 grams. Since each synthesis step has a 35% yield, and we only have one synthesis step in this Claisian condensation using the same process as the lab, we just need one synthesis step. So to calculate how much limiting reagent we need, we just have to do a simple calculation here. And that shows us that we need about 65 grams or 0.35668 moles of benzophenone. So for our reagent in excess, we want a lot of it just to make sure that all of it is reacted with our limiting reagent. So we want about 10 times the amount of moles of our limiting reagent, benzophenone, as a safe amount. So doing the calculation, we'll get about 414.3 grams of N-butyl acetate that we'll need to add in. But of course, N-butyl acetate will be a liquid at room temperature. So that's about 365.4 milliliters of N-butyl acetate. For our reagent, we use sodium ethoxide, which is dissolved in ethanol, which all of our reactants and our final product, compound M, is soluble in. For our solvent that also contains the reagent that we're using, we want a reasonable amount. We don't want to use too much in excess. So we will double the amount of limiting reagent. So if there's 1 mole per liter of reagent in our solvent, and we want about 713 millimoles, we will want to use about 713 milliliters of our solvent. Since this collision condensation is reacting 2 compounds to make 1, it is therefore thermodynamically favorable and will produce a lot of heat. So following the instructions from our lab that we did a collision condensation, we want to keep all of our reactants cool while they're doing the reaction. So to start off, we want to cool our N-butyl acetate to about under 5 degrees Celsius, and then add our solvent/reagent of sodium ethoxide in ethanol, and wait until the reaction has cooled back down under 10 degrees Celsius, and then finally add our limiting reagent of benzophenone, but in slow increments, not to overheat the reaction, all while stirring with a stir bead. After we wait probably a long time for the reaction to happen, we want to isolate our product as best we can. So we want to start with a washing. Now, the lab that we did the collision condensation used sodium chloride and sodium bicarbonate. However, we can use a washing of dichloromethane, DCM, since all our reactants and our solvent are soluble in DCM. However, compound M is not, so it's the perfect washing agent. So to try our best to get all of the reactants out, and maybe even some of the solvent, we want to do at least 3 washings with about 1/3 of the solvent that we added for each washing. So we want to wash our product with about 240 milliliters of DCM 3 times, and then extract our product. After our reaction, there might also be some water that has been produced. Now, water is also soluble in DCM. However, there might still be some stuck in the solvent. So to get rid of this, we want to use a drying agent, the same one that we used in the previous lab. We want to use enough potassium carbonate until we see small little beads running around at the bottom of our solution when we swirl it. If it's still clumping up, that means there's still water and we need to add a bit more. To separate our solution from the drying reagent, we can either use a gravity filtration system to quickly get any extra beads that might flow through with our solution, or we could just carefully decant our solution. Next, we want to try to get rid of almost all the solvent that we have left. To do this, we use the rotovap. Now, lucky for us, our solvent has a lower boiling point than water does, at around 70 degrees Celsius. However, one of the limitations in the organic chemistry lab is trying to separate compounds that have a higher boiling point than 110 degrees in a rotovap or distillation process. This is why we used a washing step beforehand, because benzophenone has a much higher boiling point than water. But even a washing or extraction is not perfect. There sometimes are extra reactants that stay in the solution even after we do them, and they won't be taken out from a rotovap. So after we finish our rotoevaporation to extract all of our solvent, there might still be some of our reactants left in it, like benzophenone. This contamination can be dealt with by recrystallization. Since our final compound M has a melting point of 68 degrees Celsius, we're going to need to let it cool down a little bit before we start our recrystallization process right after the rotoevaporation. After we do this, we want to take a small amount of our product and do a solubility test. In our solubility test, we want to use the solvent dichloromethane and ethanol, since our compound M is soluble in ethanol but not DCM, but our reactants are soluble in both. So we want to find the perfect ratio where our solid product that we got from the rotoevaporation does not dissolve in that reaction ratio mixture at room temperature. However, it does when it is heated up. So we find that proper ratio. Since DCM and ethanol have quite low boiling points of 40 and 78 degrees Celsius respectively, we want to set up a reflux apparatus so that we don't just evaporate all of our DCM and ethanol into the air. So we add our compound M product that we got from the reflux reaction into our perfect ratio of ethanol to DCM mixture and heat it up in a reflux apparatus until everything is completely dissolved. Next, we want to cool everything off to room temperature. And then after that, we want to cool it in an ice bath until a crystal precipitate forms. At that point, we then want to run it through a suction filtration to get all of our solid product out. And that will be our final purified form of our compound M. Now, to test the purity of our compound M, we can run it through an IR spectrum and see where all the peaks are. We can then do a melting point analysis and compare the IR and melting point data to literature values. Thank you for watching. I hope you liked the video and maybe even learned something. Don't forget to like, subscribe.
Toilet will not flush, the toilet will not flush, the toilet will not flush.